My name is Trung, and I'm currently a fourth-year PhD student at Aalto University in Finland. And today I will present our work in NeurIP last year about improving robustness of a neural network to corruption. So the short message here is that we show that by multiplying each individual way of a neural network with its own Gaussian random variable during training, we enhance the model robustness to distribution shift without sacrificing any accuracy on clean input or increasing the training time. So the motivation here is that neural networks are quite sensitive to input perturbation. So if you have an image of an object and then you corrupt it by just some simple short noise, for example, then the model can make a drastic change in its prediction, which make them quite unreliable in production system. So to show this, to solve this problem, then one direct way is that we can include this corruption as data augmentation during training, but people find that doing this degrade the accuracy of the model on clean input. Or in like computer vision domain, people come up with like advanced augmentation method like mix up or cut mix, for example, which does improve performance on both like clean image and corrupted images, but these are quite domain specific. So here we explore an orthogonal and domain agnostic approach, which is a feature guided input augmentation where we use the feature learned by the model during training to define the augmentation. So we will show later that this approach can be combined with any of the advanced augmentation method to further boost robustness. So the high level intuition we have is that given any input perturbation in the input space, we can find an equivalent multiplicative perturbation in the weight space, which is in the middle column here. And so from that simple observation, we think that then we can simulate input perturbation during training by sample some random noise from a distribution and then multiplying the weight of the neural network with that random noise. And we're basically transferring the perturbation simulation from the input space to the weight space. So what type of corruption are simulated by this noise? So to understand it, then we just use a simple convolution net as an example. So if we consider a first layer filter that, for example, detect a vertical line in an image, when this filter weights undergoes some point-wise multiplication with some random perturbation, the computation of the forward pass become mathematically equivalent to applying the original filter to an image where all the vertical lines in the image has been perturbed by the same noise. And we can extrapolate this to like other layer in the neural network. For example, like in an intermediate layer that detect, for example, texture or pattern, then the weight perturbation will simulate corruption of these high-level features. And then in the final layer of the convolution net, where the network typically recognize complex object through combination of simpler features, the weight perturbation can simulate structural or semantic variation of these object representation. And therefore, even though our noise distribution can be quite simple, we can still leverage the hierarchical structure of the neural network to simulate complex and also meaningful input corruption. And that is why we call this approach or this direction feature guided input augmentation. So here we provide some theorem to support our intuition. So given like a training data set in a supervised learning task and a corruption function, a neural network where omega and some loss function. So under some weak assumption about the corruption G and the loss function, there's always exists a wave perturbation psi and a constancy such that the loss under corruption is upper bounded by the loss under perturbation plus the L2 regularization term. So the two assumptions we use here is the first is that the corruption G does not change the substantially change the input, so it's bounded. And the assumption on the loss function is that the input gradient of the per sample loss is Lipschitz continuous. So this assumption is like applicable to all the loss function that we use to train neural network, because we need this so that stochastic gradient descent is guaranteed to converge. And from this theorem, then we propose our training algorithm called data augmentation via multiplicative perturbations, or DAM. So basically, the theorem in the previous slide suggests that we should minimize this following loss, which is basically the normal L2 regularization term plus the loss under this expectation, where we sample the noise from some distribution here. And the idea is that minimizing this loss function will teach the neural network to be robust to the corruption simulated by this random perturbation, which could transfer to improve robustness to real-world corruption. And yet, this new algorithm that we propose, we choose the noise distributions to simply Gaussian distributions and with mean of 1. And this variance is shared among all the random variable for all the ways. And it is a hyperparameter that we tune using like a validation set. And to efficiently estimate the expectation without like increasing the training cost, we've split each training batch evenly into M sub-batches, and then we sample a wave perturbation for each sub-batch to calculate the sub-batch gradient, and then finally we average over all sub-batch gradients to obtain the final gradient. And therefore, this algorithm is very suitable for data parallelism in multiple GPU training. So here we present some experiment results. So our baseline is the dropout method. SHAM is a sharpness aware minimizer, and also ASAM is a adaptive sharpness aware minimizer, which is like two optimization method that like promote conversion to Y minima, which has been shown to improve both generalization on like both clean input and corrupted input. And in this table, we test the train a ResNet 50 on ImageNet experiment, and then we on the ImageNet dataset, and then we test it on like various corrupted dataset, and also on adversarial example. And here we show that like if our approach maintain like a good performance on the clean test set, and then it's actually achieved like the lowest average error on a corrupted test set. And then here we test on using the same setting, but now we use a vision transformer model, which is the ViT-S16 here. And here we show that our approach also performed the best on average on corrupted error. And what interesting here is that if we use DAM with just simple basic inception style data augmentation, so just flipping or yes, it's a very basic augmentation, then we still able to train a V-vision transformer to reach the same accuracy as a ResNet 50, which is like probably the first approach that we find that can do this. because previously to train like a vision transformer to reach a good accuracy on ImageNet, there we either have to pre-train it on a like a bigger data set, or we have to use very extensive data augmentation. And then here we show that like this approach also can be used with advanced augmentation like Meetup or RAN augment to like further push the performance. Yes. So now I just want to talk about some insight about this technique. So insight number one is that there's a connection between DAM and Hessian-based way regularization. So if we take the loss function like this loss inside the expectation and perform like a second order Taylor expansion, and then if we then take the expectation with respect to the noise distribution, then it would be equivalent to the original loss plus some plus the L2 regularization of the way, and each way is now weighted by the corresponding diagonal term of the Hessian matrix. And then if we combine with the original L2 regularization term inside the dam loss, then we will have this kind of adaptive way regularization, where the way with large positive diagonal Hessian receive stronger regularization. So which I don't know like how what's kind of the effect here, but I think like if the way correspond to like large uh positive diagonal Hessian term, then probably it will have like a strong effect on the optimization trajectory. So what we're doing here is we kind of slowing down the update of this way, I guess, to make the training more stable. And then insight number two here is actually it's very easy to implement this approach. In my original experiment, I use charts from Google, but here I also provide on screen a very simple PyTorch implementation, also using the data context API of Python. So we could define like a context here that taking like out the model and then the standard or deviation of the perturbation. And then when we enter the context, what we do is basically store the original way in some dictionary, and then we perturb the way using the some random Gaussian noise here. And then as we exit the context, we restore the way of the neural network back to the original value. And then on that is on the left hand side. On the right hand side, to use this context inside a training loop is very easy. And so we basically, let's say we want to repeat this for a number of sample time, and then we just use this like convention of Python for called a context object, and then we just accumulate the gradient, and then finally we take a step in the optimizer. And then inside number three is in training and hyperparameter selection. So what I find is that we don't need to tune the way decay specifically for this algorithm. Like if you have like a default value, like a good way decay value for the standard SGD training, then just use that same value for DAM. And the only thing you need to tune is the noise variance. And we can tune it using like a validation set. One optional thing you could do is annealing the noise variance during training. We can start with a small variance and then increase it to a maximum value. And we could also learn a separate noise variance for each parameter using variational inference. And finally, I haven't tried this yet, but for fine-tuning pre-trained model with low rank, we could also perturb the pre-trained way, because the pre-trained way, like already learn a meaningful feature, so we can perturb this way specifically and not the low rank way. So during training to simulate input augmentation while optimizing the low rank parameter. So it could improve performance and like preventing overfitting, because we basically now in artificially inflating the fine tuning data set using these pre-trained features. So in summary, I just wanna restate the message or at the first slide. We found that perturbing way with random multiplicative noise during training will enhance neural network robustness to input corruption without degrading accuracy on clean input, nor increasing the training complexity. And this is a QR code to the website of the project and also our code. So that is the end of my presentation.